Greetings, this is Rob, Chief Flight Instructor for VATSTAR.com, and after this lesson, y'all come back now, you hear? Now to keep the video at a reasonable length, I'm going to go through it kind of quickly, so pause and rewind as you need to, and if you still have questions, my contact information will appear at the very end. Let's start with a few vocabulary words. Axis, that's an imaginary line sticking straight through an object which it rotates around. Here's the Earth's axis. Of course, it only spins on that one. Later, we'll be talking about multiple different axes for the same object. Degree, well, we use that word in a lot of different ways in aviation, temperature for one, but here we mean it as in degrees of an arc, so 1/360th of a circle, I guess. Now, when describing movement, we often use degrees in a sense of degrees off center. You use straight and level flight as a reference and then talk about the number of degrees left or right of that point, or up and down from level, but we'll get into that in more detail in just a bit. Now, this next word describes the main body of an aircraft, the tube-shaped area where the passengers and cargo are. Now, this isn't fuselage, okay? It's pronounced fuselage. If you imagine a plane without any of the wings or tail sticking out, that's the fuselage. Cockpit, well, that's the control room at the front of the plane where all the dials and switches and knobs and gauges are. And the pilots, obviously. Attitude, that refers to how the aircraft is pointed relative to the horizon. It could be tilted slightly nose up or nose down, or tipped over to one side, or even some combination thereof. And if you have a bad attitude, you may require an attitude adjustment. The way you adjust your attitude is through control surfaces. Those are hinged panels on the outside of a plane that deflect air and change the way the plane is pointed. They change its attitude. Here's an example of the control surfaces on the wing of an airplane, and as you can see, they deflect the air up or down, which changes the way the plane is tilted with respect to the earth. These control surfaces are manipulated by controls in the cockpit, either by the pilot or in some cases by the airplane itself. And we'll come back to that and talk in more detail about what those are called and how they work later on in this lesson. Next, joystick. Well, duh, that's a control stick that plugs into your PC. Now, a proper joystick for flight simulation has two important properties. First, it's got to detect a range of motion. If you think about old school arcade game joysticks or control pads, you had 9 possible directions: up, down, left, right. Any of the 4 diagonals are centered, and that was it. When you move the stick in a direction, it was all or nothing. That doesn't work well for flight simulation. You've got to be able to tilt it slightly to the side or fully to the side or anywhere in between in any direction. The other thing is, when you let go of it, it has to center itself. Whether it's spring-loaded or has elastic bands inside it or whatever, it has to stay centered when you're not touching it. It can't be falling all over to one side or whatever. It's helpful if it has buttons and other switches and controls on it too, but it's not absolutely mandatory. Control yoke, that's a U-shaped steering wheel of sorts made specifically for controlling an airplane. And again, these usually plug in via USB, and again, a lot of them have levers and knobs and switches and buttons on them too, which is good. This one pictured here, it's actually the model that I use, and it's a good balance of affordable but still decent quality. Now note, when I say U-shaped, that's just because it's probably the most common design for aircraft control yokes, not just in flight simulation, but also in the real world. But it's not the only design. Boeing and Cessna in particular are two very popular aircraft manufacturers who seem to swear by the traditional U-shape, but there are others as well, like this figure 8 looking one, which is, I don't know, kind of just a U-shape with support beams on the top end, really. There's also this weird looking thing here, and don't even talk to me about the crazy Embraer jets. But this U-shape is pretty classic and comfortable to use, though a joystick works just as well for less money and is perfect for a beginning sim pilot. Whatever you do, don't try to fly by keyboard alone. You might think it's less complicated, but it's not. A beginning sim pilot really needs a joystick, and you can get a decent used one for around 20 bucks US, and if you end up not sticking with the hobby, it's still good for other games like sports or first-person shooters or whatever. But flying by keyboard is really very, very tricky, and if that's how you try to learn from the beginning, you're most likely going to just get frustrated and quit. So a joystick is well worth the relatively meager investment, trust me. If you really get into simming, maybe you can buy something nicer down the road, but honestly, a cheapy joystick is all you truly need to enjoy the hobby. As a matter of fact, I did it that way for decades before buying my little control yoke system just within the last couple years. But anyway, where was I? Oh yeah. So the main topic of this lesson is the 3 axes of movement. Axes, by the way, A-X-E-S is how you say the plural of axis. We're not chopping up any firewood here. But here's our aircraft, and here are the 3 ways it can rotate. First is the roll axis. Stick a tube right down the length of the fuselage, just like a hot dog on a rotisserie, and spin it from side to side, and you're rolling the aircraft. When the passengers lean to the left or the right, one wing raises while the other one lowers. That's the roll axis, and here's how the plane looks when it rolls. Next is the pitch. That's how nose up or nose down the plane is, and we've touched on that already in the last couple lessons, but here's a plane that's pitching up and down a few times. Finally, the yaw axis. If you think about a car turning on a flat road, that's rotation on the yaw axis. Now, obviously, the body of the car rolls a little bit too, but mainly it's turning on the yaw axis. Now, planes don't typically turn in this fashion, but we'll talk about why in a later lesson. Bonus points, by the way, if you know the terms longitudinal axis, lateral axis, and vertical axis. Pat yourself on the back. Yay! For our purposes, though, roll, pitch, and yaw are perfectly sufficient. When we talk about roll and pitch, we measure it in terms of degrees, and more specifically, degrees off of center. The terms roll and bank, by the way, are essentially interchangeable. Think of a banked turn on a racetrack. The vehicle is tilted to one side as it navigates the turn. So think of 0 degrees as being perfectly wings level, and theoretically, 90 degrees would be completely sideways. Now, unless you're performing aerobatics or are in a military plane engaged in combat, you're most likely going to be limiting the bank angle to 30 degrees. That's about as steep a turn as you're going to see in commercial or recreational flying. Pitch, like we've touched on in earlier lessons, refers to how nose up or nose down you're pointed. 0 degrees of pitch is level, pointed straight at the horizon. Positive pitch is nose high, and negative pitch is when the nose is pointed down toward the ground. And again, 90 degrees would be straight vertical or straight down toward the earth. But in reality, we're generally not going any steeper than about 20 degrees up or 10 degrees down. And even those are fairly extreme for regular flying. You'd normally only go to around 15 degrees nose up during takeoff, and then after that, the most you'd usually use is like 7 or 8 degrees. Descents, you're probably not going any more nose down than about 5 degrees most of the time. But believe me, the passengers feel exaggerated pitch effects, so 20 degrees nose up probably feels to them more like 50, and any more than 5 degrees down gets them started reciting prayers. So now we know how to describe an aircraft's movement on the 3 axes. How do we control it? Here's a nice little chart which will help us pair an axis or direction of movement with the external control surface that controls that movement with the cockpit control that directs that control surface. So first, roll. Like we showed you earlier, roll is controlled by the surfaces on the wings. Those are called ailerons, and they deflect air up and down off of the wing when the stick or yoke is moved left or right. They work in opposition to each other, so when the right one moves up, the left one moves down, and vice versa. So watch as I move the joystick left and right. In the cockpit, that's going to look like this. Or maybe I have a control yoke and it looks the same as what's on the screen here. Here's what that does to the ailerons. And like I said, the ones on the other side of the plane are doing the opposite from these. And from the back, that will look like this as the aircraft turns on the roll axis. Watch the ailerons this time and see how they're working in opposing pairs. Next is pitch. Pitch is controlled by the horizontal moving surfaces on the tail, which are called elevators. If it helps you to remember, at least in the US, in a tall building, an elevator is what helps you go up and down. Of course, you crazy Brits and Aussies and Kiwis call that a lift, so don't confuse yourself. Elevators are controlled by moving the stick or yoke forward or back. So here's me moving the stick forward or back. And here's what that looks like in the cockpit with the control yoke. And finally, the effect that'll have on the plane. Notice the elevators on the tail and how they move to deflect the air. Quite the roller coaster ride. Now, real quick before we get into the last axis, note that when you push the stick or yoke forward, that's pushing the nose down. This goes to the opposite of old school joystick logic, where forward was considered up. So if you think of the stick more as standing upright rather than facing you, then between the ailerons and elevators, pushing the stick in any direction will cause the aircraft and its occupants to lean in that direction. So that should make it a bit more intuitive for you. So finally, yaw. Yaw is controlled by the rudder, which is the vertical surface on the tail swinging back and forth. In a real plane, the rudder is controlled by a pair of pedals that work in opposition to one another. When you slide one forward, the other slides rearward and vice versa. We'll get a look at that in just a second. Now, in flight simulation, there are 3 main ways to control the rudder. The first would be simply to buy a set of USB pedals made for the exact purpose of simulating rudder pedals. But not everyone can afford that, especially when you're just starting out in the hobby. A more common way is with a joystick that includes a twist axis. Even some relatively inexpensive ones, like this one, can be twisted back and forth in addition to leaning it from side to side. The pedals in the cockpit look like this. Look at the floor in front of the yoke and notice how when one moves forward, the other moves back. Not that you'd ever actually turn an aircraft this way, but if you did, this is what it would look like from the outside. When you push on the right pedal, the back of the rudder moves right, which pushes the nose to the right, and vice versa. So the nose of the plane is going to go toward the side you're pushing on. Now, if you don't have pedals and you don't have a twist axis on your joystick, that's okay. A lot of beginners don't, and even some long-time sim pilots don't. There's a sort of cheat in the control settings of most simulator software. It's called auto coordination. Having that option active is essentially going to create an artificial link between your ailerons and your rudder, so that moving the stick from side to side is going to control both at the same time. Now be careful. When we get into a later lesson, we're going to talk about the mechanics of a proper airborne turn, and in that we're going to discuss turn coordination. That's not the same thing as auto-coordinating the rudder and ailerons. It's close, but it's different. So keep that in mind for later. But for now, just know that using auto-coordination is a way to control your rudder if you don't have pedals and your stick doesn't twist. Next, let's talk about some other important control surfaces. These don't affect the three axes of movement as such, but they're still critical for aircraft control. First is flaps. One might say flaps and slats. Flaps are on the trailing edge of the wing, sort of near the ailerons, and slats are on the leading edge of the wing. They're kind of hard to see, so hopefully this will help. So what they do is to allow the pilot to extend the curvature of the wing, and here's a shot of that in action. Now, nearly all planes will have flaps, which are the ones on the back. Slats are found on most airliners and a few medium-sized planes, but not usually on single-engine piston aircraft. Did you notice how they worked in tandem with each other? They extended and retracted at the same time. That's pretty much how they operate. In fact, I don't know of any planes where you can extend one without the other. You extend the flaps, and the slats just follow along and do their thing. In fact, most of the time, you don't even really refer to them separately. You kind of just say flaps, and if your plane has slats, it's just understood that you mean both. But the point is, extending the wing curvature gives that plane more lift at slower speeds. They're extendable in increments, and different planes have different number of increments. Some planes only have 2 or 3. A lot of airliners and larger planes might have as many as 7 or 8 different settings. The first few settings add mostly lift and some drag, but the deeper you get, you're adding more drag and only a little extra lift. So these are mostly used during takeoff and landing. For takeoffs, you probably use only a small amount of flaps because you want a little extra lift without a lot of extra drag. And when approaching to land, you're probably using most, if not all, of your flaps deployed all the way out or nearly so, because you want to come in at a nice, slow, safe speed. But you also want a lot of drag because you want to be able to control that speed. When you pull the throttle back, you want there to be enough drag that the plane just slows itself down, because precise speed control is crucial during landing approaches. We'll talk more about that in a later lesson as well. Next, spoilers. These are panels that the pilot can extend upward into the airflow. Here's how they look in action. On most aircraft, they can be partially or fully deployed in the air or on the ground. They're also known as speed brakes or sometimes aerodynamic brakes or even simply air brakes. And most medium to large size aircraft have them, and even a few smaller ones do. The idea is that they help slow down the plane by increasing drag, but in a way that doesn't stall the airflow over the wings. In the air, this helps control the aircraft's speed during descent. On the ground, they're usually fully deployed to help slow down after touchdown. The plane has to brake kind of rapidly to make sure you can stop within the runway length you have available, so you'll use full spoilers, full flaps, and thrust reversers if you have them, and all of that helps slow the plane down while conserving the use of the wheel brakes. Wheel brakes can overheat and even catch fire when you use them with too much force, so it's good to use as much aerodynamic braking as you have available. Finally, the throttle. Most half-decent gaming joysticks have a lever on them somewhere that's meant to be used as a throttle control. On this model, the throttle lever is right here. The throttle is not technically a control surface, but I included it in this lesson because controlling the throttle is critical for maintaining control of the aircraft. The throttle, much like a gas pedal in the car, regulates how much power the engine is producing. Now here's how that translates into the cockpit of the plane. In many small aircraft, such as this Cessna Skyhawk, the throttle is this little pull-out knob. Pushing it forward increases the engine power, and pulling it back out reduces it. In other planes, like this Boeing 737, the throttles are levers that you push forward or rearward. Notice that in multi-engine aircraft, you're actually going to have a separate throttle control for each engine, but you usually apply them all together, and generally in flight simulation, your one throttle control will be mapped to all of them, whether it's 2, 3, 4, or more. Later on, you can buy fancier and more realistic sim controls which allow you to manipulate them independently, but even still, the vast majority of the time, you're moving them all in tandem, so a single control really is more than adequate. So, let's quickly summarize the key points. Moving the stick or yoke left or right controls the ailerons, which causes the plane to bank on the roll axis. Moving it forward or back controls the elevators, which causes the plane to pitch up or down. The rudder is controlled by pedals, but that might be mapped to your joystick's twist axis, or might be auto-coordinated so it automatically moves in tandem with your ailerons. And the rudder controls the plane's movement on the yaw axis. Additionally, flaps and slats, which you can refer to generically just as flaps, extend the wing's curvature, adding both lift and drag, allowing the plane to fly more slowly, especially during landing approaches. Spoilers, also called air brakes or speed brakes, add aerodynamic drag, which helps control speed during descent or to brake after touchdown. And the throttle, which isn't technically a control surface but still very important, controls how much power your engine's putting out. Got it? Good. If you have any questions, shoot them over to me in an email to cfi@vatstar.com. We'll see you in the skies.